In this video, we will be finding various key elements of the function f of x equals 1 over x plus 2 squared. So the first element that we're going to find are the zeros. They are any point that lies on the x-axis. So to find the zeros, we will want to set the top of the equation to 0 and solve. In this particular equation, you can see that the top of the equation is 1. So 1 equals 0. Because the top of it will never equal 0, we can say that there will be no zeros in our graph. The next key element that we will find are the critical points, which are the values of x for which the derivative f prime of x equals 0 or is undefined. To find these points, we will first want to derive our original equation, which is 1 over x plus 2 squared. When we derive this, we will want to rewrite because it will make it easier. So if we rewrite it, we can cross the line and change the sign with the exponent, being left with f of x equals x plus 2 to the negative second. Okay, so we will start to derive this using the chain rule. So we'll bring down our negative 2 to the front. X plus 2, subtract your exponent by 1 is negative 3, and don't forget to derive the inside. This case, it doesn't really matter because it's just 1, but in other cases you will want to remember to derive the inside. So we are left with negative 2 x plus 2 to the negative third, and we'll rewrite that to get rid of the negative in our exponent as negative 2 over x plus 2 to the cubed. The next step to finding your critical points is to set this equation equal to 0. So we took our f prime of x and set, because the top will never equal 0, we just set the bottom equal to 0. So x plus 2 cubed equals 0. Cubed root both of these sides to get the cubed away. So we're left with x plus 2 equals 0. Subtract 2 from both sides and you end up with x equals negative 2. And in this case it will be an asymptote because that is a point where the graph is undefined. Next we're going to find the relative extremum, which are the peaks of hills, lowest points of valleys, or high endpoints. Because all of these happen at critical points, we will plug in our critical point, which was negative 2, back into our original equation to get our y value. When plugging negative 2 back into the original equation, we will find out that it is undefined. So this shows us that there are no relative extremums on our graph. Other key elements we need to find are the increasing or decreasing intervals. To find these, we must create a sign line with a critical point x equals negative 2 that we found earlier. So here is our sign line, and here is negative 2 that we put on it. Now the next step is to plug in values to find out what the sign is on each side of this number. So we can plug in any number between negative infinity and negative 2 to get the sign of this because we aren't worried about the number. So I plugged in negative 5, for example, and ended up with a positive number. So I did write plus up here for positive. On this side, we can plug in another interval between negative 2 and infinity to find the sign for that, and you can plug in any number that's above negative 2, so I plugged in 6 and I got a negative. As you can see, this sign line tells us that from negative infinity to negative 2, our intervals are increasing, and from negative 2 to infinity, our intervals are decreasing. Inflection points are the next thing that need to be found. They are points where the slopes or tangent lines of our graph change from positive to negative. Every derivative's graph will cross this same point. So to find this, we will derive our f prime of x that we found earlier for another time. In this one, it will benefit us to rewrite it once again. So we will rewrite it as f prime of x equals negative 2 x plus 2 to the negative third because we did cross the line and change the sign with this negative 3. So to derive, we will want to use a chain rule again. So leaving our negative 2 out front, we will bring our negative 3 down. X plus 2 and subtract your exponent by 1 gets you negative 4. Derive the inside gives you 1. So we are left with negative 2 times negative 3 is 6. X plus 2 to the negative 4th. Rewriting this to get rid of this negative in our exponent, we will end up with f double prime of x equals 6 over x plus 2 to the 4th. The next step to find our inflection point is to set the bottom of this equation equal to 0 because once again the top will never equal 0. So we will fourth root both sides of the equation to get rid of the 4 here. So we will end up with x plus 2 equals 0. Subtract 2 from both sides, and you will see that our inflection point once again is at negative 2. The last key elements that we need to find are the intervals in which our graph is concave up or concave down. So to do this, we want to create a sign line using our inflection point that we found earlier, which is negative 2. So here is our sign line with negative 2. We can plug in any point between negative infinity and negative 2 to get the sign, and any point that you can plug in, you will find out that it is positive, and any point from negative 2 to infinity is also positive. So from this sign line, we can conclude that from negative infinity to negative 2, our graph is concave up, and from negative 2 to infinity, our graph is also concave up. Although we cannot say that from negative infinity to infinity that our graph is concave up, because we do in fact have an asymptote at negative 2. So during this video, we have found zeros, critical points, relative extremums, increasing and decreasing intervals and inflection points, and concave up and concave down intervals of the function f of x equals 1 over x plus 2 squared.